In this lecture, we're going to talk about something called 3D, or generalized Hooke's law. You may remember one-dimensional Hooke's law that we've talked about previously, and it's worth reviewing that. So we're going to review the 1D Hooke's law. So you may recall when we talked about having a tensile specimen, putting an axial force on it, we can generate a stress in the material, and the axial stress is the force divided by the cross-sectional area. At the same time, we end up having a strain in the material that we can find from the change in length divided by the initial length. These are both in the axial direction, and we can construct a stress-strain curve. As we apply force, we get strain. And for most materials, many materials like metals, initially there's a linear relationship between stress and strain up until we get to something called a proportional limit stress. The slope of this curve is known as the modulus of elasticity. Some people call it Young's modulus. And we can construct an equation of a straight line that describes this curve, and that would be sigma is equal to E epsilon. It's very similar to the equation of a line. Y is equal to mx plus b, except instead of using x and y axes, we're using sigma and epsilon axes, and the slope of the line is capital E with an intercept of 0. Another thing happens when we pull on a bar, and I'm going to draw this bar sideways this time. And that's that when we pull on this bar, it not only gets a little bit longer, but it also shrinks in a little bit due to Poisson's ratio. So let me exaggerate this quite a bit. Trying to draw a straight line. To show that we not only get a change in length, but we can also get a change in diameter or a change in thickness of our round bar. And that the term called Poisson's ratio is defined as the negative of the diametral or the transverse strain divided by the axial strain. All right, now let's take a look at a cube of material pulled out of a three-dimensional object, and we're going to apply stresses in each of these three different faces. Let me use some different colors here. Let's start off first by applying just a stress in the x direction. We'll have a coordinate system. This will be the x, the y, and out here, the z directions. So we'll have a stress sigma x. Now we know that we're going to get a strain in the x direction, and by rearranging our 1D Hooke's law, that stress over the modulus of elasticity gives us the strain in the x direction. In the y direction and in the z direction, we also get some strain because of the Poisson ratio of the material, that Poisson contraction. It's going to be minus nu times the axial strain, or in this case the x strain, with the x strain given by sigma x over E. I'm leaving a little space here on purpose. That happens both in the y and the z direction, a negative sign indicating contraction. All right, now let's forget about the x direction stress for a moment, and let's think about what happens when we apply stress in the y direction. When we apply stress in the y direction, we get a strain in the y direction we apply a tensile stress, we get a positive strain. The amount of that strain is going to be given by sigma y divided by the modulus of elasticity E. We also get contractions in the other two perpendicular directions. In the x direction, we get a Poisson contraction, which would be minus nu sigma y over E, and minus nu sigma y over E in the z direction. Lastly, let's apply some stress in the z direction. We're going to forget about the other two. When we apply stress in the z direction, we get an extension in the z direction, sigma z over E, and a Poisson contraction in the other two directions, minus nu sigma z over E, and minus nu sigma z over E. Now, we talked about applying these in three different directions independently. If we were to take this cube of material and apply all of these things at the same time, then we'd have extensions and contractions from the other stresses. They would add or superimpose upon each other to give this set of equations that I have here. So if I have both sigma x, sigma y, and sigma z, in the x direction I get an extension from the sigma x, and I get Poisson contractions from the sigma y and sigma z stress. Likewise, I have in the y direction, epsilon y is equal to sigma y over E minus nu sigma x over E minus nu sigma z over E, and then a similar equation for the z direction. There are some assumptions that we've made in constructing these equations. First thing is that we've assumed that we have an isotropic material. Iso means the same, tropic is direction. We're assuming that our material behaves the same in every direction. This is a pretty good assumption for a lot of engineering materials. However, there are also important materials that are not isotropic. The word for that is anisotropic. Things like carbon fiber composites, heavily processed metals that are elongated in their grains with texture, those things can be fairly anisotropic. The assumption that we're going to make in our class now is that the materials that we're going to deal with at this point are isotropic materials. The other assumption that we've made that we need to explicitly state is that we're assuming that we have a linear system. For us, that means a linear material or a linear elastic material, such that we can use the concept of superposition. This is part of what's known as 3D or generalized Hooke's law. In addition to this, we can throw in strains due to temperature. So we know the thermal strain is alpha delta T. We can include that on each of these expressions as well. And we can also apply more than just normal stresses in our material. We can apply shearing stresses as well. Shearing stress that is on the x face and points in the y direction is known as the shear stress tau xy. It exists all the way around the block or the cube. We already know that shearing stresses have to be in a set to keep equilibrium. So we can calculate the shearing strain from Hooke's law in shear. Tau xy would be equal to, gamma xy would be equal to tau xy divided by the shear modulus G. And likewise, I won't draw it on the picture, but we can have a shearing strain, gamma xz, equal to tau xz divided by the shear modulus G, and gamma yz equal to the shearing stress tau yz divided by the shear modulus G. If you remember, the shear modulus is the slope of the shear stress strain curve. Again, we're assuming that we have what's known as an isotropic material. For an isotropic material, it turns out that there's a relationship among the elastic constants E, G, and nu Just to write that on this page so you have it handy, the shear modulus G is E over 2 divided by 1 plus nu. The last thing we need to talk about, and then we can do a couple of examples, is that whenever you have a uniaxial stress state, you can use 1D Hooke's law. Whenever you have more than one stress component, or a multiaxial stress state, you must use 3D Hooke's law. 3D Hooke's law will work in a uniaxial stress state as well. So that's why we call it generalized Hooke's law. It's the more general version. It will work for an isotropic material that's linear elastic in all the cases that we have, 1D, 2D, or 3-dimensional stress states. Okay, so let's label this as 3D Hooke's law. These equations can look intimidating. We got 6 equations, but I do want to point out that they're very similar. It's just kind of like you're cycling through the subscripts on these equations. If you lead off with the epsilon x term here, then you'll have the sigma x term in this position divided by E minus nu times sigma y over E minus nu sigma z over E plus the thermal strain. And if you want this y strain, then your stress will be the y stress in this position minus the other 2 Poisson contractions and so forth. So it's really not as bad as what it might look when you first see these 6 equations. So for an example, let's take a look at this stress state. We have a little block here. It's a square. It's really in 3 dimensions, but we're just looking at it down the z-axis. We have sigma x equal to 200 megapascals, sigma y equal to 100 megapascals, and tau xy equal to 50 megapascals. We want to find all of the non-zero strains. So this is also known as a state of plane stress. Let's talk about that for a minute. A state of plane stress is a situation you get where all the non-zero stress components lie in one plane. Most books usually make this the x and y plane, but it can be x and z or y and z, whichever plane it is. That's the plane where you have the non-zero stress components. So if we want to use 3D Hooke's law to find the strains, we're going to write down, let's just write down the equation first. Epsilon x is sigma x over E minus nu sigma y over E minus nu sigma z over E. There's no temperature change, so I'm going to leave that off. Sigma x is given as 200 megapascals. I'm going to write everything in pascals. The modulus of elasticity is 210 gigapascals. Giga is 10 to the 9th. Minus Poisson's ratio, 0.3, sigma y over E. And in this particular case, sigma z is equal to 0. Epsilon y is going to be sigma y over E minus nu sigma x over E minus nu sigma z over E. And we can plug those numbers in as well. We have 100 times 10 to the 6th divided by E, 210 times 10 to the 9th minus 0.3, 200 times 10 to the 6th divided by 210 times 10 to the 9th. We'll get those numbers in just a moment. Now some things, sometimes I see people leave off the strain in the z direction. You do have strain in the z direction even though the stress is 0 in a state of plane stress. the thickness of the plate or the thickness of the material can change because of the Poisson contractions in the material. So let's go ahead and write down epsilon z. In general, it's sigma z over E minus nu sigma x over E minus nu sigma y over E. In this case, it's going to be 0, because sigma z is equal to 0, minus nu sigma x over E minus nu sigma y over E, and that's 100 megapascals. Now we're not quite done yet. We're also going to find out the shearing strain gamma xy. Shearing strain gamma xy is tau xy divided by the shear modulus G. The shearing stress in this case is 50 megapascals, and the shear modulus G we can find from E over 2 divided by 1 plus nu. All right, let's find out what all those numbers are. Okay, putting those numbers into my calculator, I got epsilon x is equal to 810 microstrain. Epsilon y is 190.5 microstrain. Epsilon z is negative 429. That means that the thickness is shrinking when we pull on it in those two directions. And gamma xy is 619 microstrain. The sign of the stress is very important to get into the right end of these equations. If you have a tensile stress, you have a positive stress that you put into the equation. If you have a compressive stress, you put in a negative number. Okay, let me make a new page here and let's emphasize that. Okay, so here's our coordinate system. We have a sigma x, sigma y, and tau xy. These are the directions for positive values for those three stresses. So positive stresses are tensile stresses. Negative stresses are compressive stresses. Okay, so this is for the sigmas. And a positive tau xy is on the plus x face, and it points in the plus y direction. So this would be a positive shearing stress that I'd use in my Hooke's law equations. If I had a state of stress that looked like this, then I would use sigma x equal to minus 300 MPa into my Hooke's law equations. I would use sigma y is equal to plus 100 MPa in my Hooke's law equations, and my tau xy would be a minus 30 megapascals into those equations. All right, let's take a look at another answer. Sometimes, at another question, sometimes we know what the strains are in the material, and we want to find out what the stresses are. Okay, so here's a typical question like that. So here we have a state of plane stress. We want to figure out what sigma x, sigma y, and tau xy are if we know the strains, epsilon x and epsilon y, in the material properties. We also know the shearing strain, gamma xy. We can use that to find the shearing stress, tau xy. After we find those in-plane stresses, we want to find out what the strain is in the z direction, epsilon z. All right, so we're going to set up our 3D Hooke's law. Let's work it with symbols first. So we're going to have epsilon x is equal to sigma x over E minus nu sigma y over E. And because sigma z is equal to 0, I'm not going to include that third term. Epsilon y is sigma y over E minus nu sigma x over E. And again, since sigma z is equal to 0, I'm not going to include that term either. We want to be able to invert these equations. Now, you can plug in the numbers at this point and do this, but let's go ahead and do this in terms of symbols, and we're going to get some equations. I don't want you to memorize those, but I want you to see how we can get those from our basic 3D Hooke's law equation. If I take the bottom equation and the top equation, I multiply both sides by E, I will get E epsilon x is equal to sigma x minus nu sigma y. And likewise, on the bottom, E epsilon y is equal to, I'm going to move it here, sigma y minus nu sigma x. If I take and multiply the bottom equation by Poisson's ratio and add the two equations together, I'll get the sigma y terms eliminated. And I'll factor out the sigma x over there on the right-hand side. Then if I solve for sigma x, what I'm going to get is capital E divided by 1 minus nu squared times the quantity epsilon x plus nu epsilon y. If I were to do the same thing and eliminate sigma x, I can get an equation for sigma y. It's basically identical, with the exception of the subscripts being changed. I'd have epsilon y plus nu epsilon x. So I can put the values for my elastic constants and the strains and find my stresses, sigma x and sigma y. Of course, the shear modulus G can be determined by E over 2 divided by 1 plus nu. So I can find my shearing strain equal to tau xy over G. I can rearrange that and find that tau xy is equal to G times the shearing strain gamma xy. And the shearing strain is given. Once I determine what sigma x and sigma y are, I can then find out what what epsilon z is. Epsilon z is sigma z over E minus nu sigma x over E minus nu sigma y over E. But since this is a state of plane stress, sigma z is equal to 0. Once I found sigma x and sigma y, then I can get epsilon z. All right, and you can check me on these, but what I got was sigma x is equal to 54.4 megapascals. Sigma y is minus 108.8 megapascals. That should say tau xy is 20.4 megapascals. And the strain in the z direction is 80 microstrain, 80 times 10 to the minus 6. Micro means 10 to the minus 6. And just to wrap everything up, these 6 equations are known as 3D or generalized Hooke's law. We talked about the sign convention for stresses. We talked about how we have to have a linear elastic isotropic material. We talked about the shear modulus G being equal to E over 2 divided by 1 plus nu. We've talked about that in the previous lecture. And then how we can start either with stresses and plug them into this equation to find strains, or we can find strains and use these to find stresses. For me, I would never give an exam where you'd have to invert 3 equations and 3 unknowns. I would always have a state of plane stress if I gave you strains and asked you to find stresses. Otherwise, the algebra gets to be a little bit too cumbersome for a regular exam. One last thing that you can do with these is once you know strains, we can always go back and relate that to changes in lengths. So if you had a plate, you can say that the change in length in the x direction divided by the original length in the x direction is the strain epsilon x. And you can find final dimensions of a plate, or you can find changes in dimension by rearranging these formulas.